Welcome to the session about the fluid simulation. And today we have invited two speakers, Professor Yoshinori Dabashi from the Hokkaido University, Japan, and Professor Bo Ren from Nankai University, China, to give us a talk. So the first talk is about the fun with fluids by Professor Yoshinori Dabashi from Hokkaido University, Japan. Yoshinori Dabashi is a professor at the Hokkaido University in the Graduate School of Information Science and Technology, Japan, since 2020. His research interests center in computer graphics, including lighting simulation, fluid simulation, digital fabrication, and sound synthesis. He received his BE, ME, and PhD in engineering in 1992 and 1994 and 1997, respectively, from Hiroshima University. He worked at the Hiroshima City University from 1997 to 2000 as a research associate. His work has been awarded from the Eurographics, the Society for Art and Science, etc. He received the Commendation for Science and Technology by the Minister of Education, Culture, Sports, Science, and Technology in 2014. So now, let's leave the time to the talk by Professor Dabashi.
Okay, thank you. Let me share the screen. Yes, can you see the screen? Okay, let's start. Yes. Okay, thanks for the introduction today. I'm going to talk about some of our research related to the fluid simulation. Yeah, title is the fun with fluids. Okay, the fluids, we see fluids everywhere in our daily life. For example, we see smoke, water, and fire, and so on. So actually, fluids are very familiar with us, and the appearances of and the motions of those fluids are very interesting and attract many people's attention. So it is very natural for us computer graphic researchers to work on the visual simulation of fluid phenomena. And in computer graphics, we often employ a physically based simulation to create realistic animations. So that is, the methods developed in computer graphics are usually based on the numerical solution of Navier-Stokes equations. So shown in this slide. So we are mostly interested in the incompressible Navier-Stokes equations, which are shown in this slide. And we have two partial differential equations. The first one describes first one is actually the equation of motion, and the second one is the mass conservation condition. Anyway, by solving these these equations numerically, we can obtain the motion or velocity of the fluid, or we can also obtain the pressure field. So we have been working on the fluid simulation so far, and this slide shows some of the research results obtained by using our previous method. We've developed for the simulation of cloud formation, or simulation of smoke, or elastic viscous fluids, and ice melting, and so on. And more recently, many researchers have developed a much more complicated or sophisticated method for simulating complicated different physical phenomena, fluid phenomena, as shown in this slide. So by using these methods, we can create highly realistic, complicated animations of different fluid phenomena. However, we believe that there are still fundamental problems remain with the fluid simulation, which are shown in this slide. The first one is the computational cost. So the fluid simulation is actually very time consuming. So it is not surprising that we need several seconds or tens of seconds, or sometimes several minutes for each time step of the simulation. And the second problem is the directability. That is, in some applications, like in entertainment applications, movies or video games, the artists or animators are often requested to produce desired visual effects. However, this is actually difficult for fluid simulation. we have to repeat the simulation with a different parameter setting, and the simulation computation time is usually very long. So this parameter adjustment process is really tedious and time consuming. So we have been focusing on the second problem, and we have developed a set of methods listed in this slide. We developed a method for controlling a simulation, image-based approach, and we have developed a method for editing a fluid simulated data set. Sorry. And recently we developed a guided simulation method. So today in the following, I would like to talk about some of these, and I would like to show you some interesting examples. So let me start with the first one, the controlling the simulation. So controlling the fluid simulation was firstly developed by Trey et al. In 2004. In this case, they use external forces to control the smoke simulation. This one is a example of this method. In this case, the smoke forms the shapes of the letters of SMOKE. So we are inspired by this method, and we wanted to extend this method to a natural phenomena, in our case, clouds. So this slide shows an overview of our system. So in our system, the user first draws a contour line, this pink curve of the desired shape of the clouds. And then our system controls the simulation so that the final shape of the synthetic clouds becomes the same as the shape specified by the user. So we first tried to use the external forces like the method mentioned in the previous slide, but we found that the external forces are not very good for our case. So using external forces often results in unnatural motion and shapes of the cloud. Instead, our method controls a sum of the physical parameters involved in the numerical simulation. Let me talk about some of the details of this method. Firstly, I would like to talk about an overview of the cloud formation process in the real world using this slide. So when there are no clouds in the sky, the ground is heated by the sun. And then the air near the ground starts to move upward due to thermal buoyancy force. And as these air parcels move upward, their temperature decreases due to a phenomenon called adiabatic expansion. And finally, at a certain altitude, a phenomenon called phase transition occurs. That is, water vapor becomes water droplets. And these water droplets are perceived as clouds. And furthermore, when the phase transition occurs, a so-called latent heat is generated. And this latent heat creates additional buoyancy force. And this additional buoyancy force promotes further cloud growth into higher regions. So these are the phenomena involved in the cloud formation. So these phenomena can be described by these 6 partial differential equations. So first two are actually the Navier-Stokes equations, and the third one is the buoyancy force, and the fourth one represents the temperature of the atmosphere, and the last two are related to the phase transition between the water vapor and the water droplets. So by solving these equations numerically, we can obtain this kind of animation. So in this case, we try to create a kind of realistic animation of the cumulonimbus formation. So we repeat the simulation many times to create this animation to adjust the parameters in the simulation. So it is very time consuming to create this kind of animation. So we want to address this problem. So through a number of experiments, we found that the shape of the clouds can be controlled by adjusting this one, the amount of latent heat. So as I mentioned in the previous slide, the latent heat promotes further cloud growth into higher regions, so we can adjust the height of the clouds by controlling the amount of latent heat. However, the latent heat is not generated unless the phase transition occurs. So therefore, additionally, we decided to control the phase transition process. Particularly, we actually add certain amount of vapor to promote the phase transition. Anyway, we developed two controllers for these two variables, and by using these controllers, we can control the generation of clouds and vertical cloud development. And the one important feature of this method is that we do not use external forces. So we call our method is a kind of implicit control. So this implicit control tries to preserve the dynamics of the cloud formation as natural as possible. So we believe that this method can create realistic animation of the cloud formation process. Okay, now let me show you some results. But first, I would like to show you a comparison between the results using the external force and the results using our method. So let's see first this one, results using the external force. So this pink curve indicates the target shape. So although the target shape is formed, but the motion of the clouds is not realistic very much. So let's see then our method. In this case, the clouds naturally grows, and the shape, the clouds finally forms that tight shape. Okay, now let me show you some more practical examples. In this case, we try to generate typical cloud shapes that are often observed on a hot summer day, like this one. This is a target shape specified by the user. And then now the simulation is controlled. And finally, the target shape of the clouds is formed. Next one, in this case, we use a photograph to control the simulation. So this is the photograph of real clouds, and we manually extract the contour line of these clouds and use the extracted contour line to control the simulation. This is extracted contour line. So here is the controlled simulation. So if you compare the shapes of the synthetic clouds and the real clouds, the overall shape is similar. So I think we can, this method can be considered as a kind of image-based modeling of the clouds using the simulation. The last one, in this case, we try to create kind of unnatural clouds. In this case, skull-shaped clouds by creating two holes inside the clouds. This is the target shape specified by the user. This is a holes. And in this example, we actually use some external forces around these holes in order to prevent the clouds coming into the inside these holes. However, overall shapes and motion of the clouds are kind of realistic because our method tries to simulate the cloud formation process as naturally as possible. Okay, that's the first one. Okay, next one, I'd like to let me skip the second one. If you are interested, I can show you later. So let me ask after the talk. So let's move on to this one, editing approach. So in this case, fluid simulation is expensive. So in this approach, we wanted to reuse the simulated data set for different scenes by modifying the simulating data set. So this picture shows an example of this approach. So we see 3 streaks of the smoke rising from chimneys, 3 chimneys. So among these, the one is simulated by solving the Navier-Stokes equation, and the other 2 are generated by editing the simulated one. And the answer is like this. The leftmost one is actually simulated with the time-consuming simulation, and the other 2 are generated by deforming the leftmost one. So this looks good, but the natural question is that, so are these deformed smoke realistic or not? So however, this question is difficult to answer because we have no clear definition of the realism of the synthetic smoke. So instead, we replace this question like this one. So are these physically reasonable or not? This question can be answerable because we have some equations for computing the motion. So in this particular case, we designed the deformation method so that this condition, mass preservation condition, is satisfied. So our editing approach is based on this concept. And recently, we have developed 2 approaches based on the idea described in the previous section. The first one is a flow interpolation, and the second one is a style transfer. So I would like to talk about the first one only today. The first one is actually an interpolation technique, and the second one is a kind of extension of the texture synthesis to the velocity field. Yeah, let's move on to the first one, this one. So this one is mainly done by this person, Shuhei Sato, who graduated from my laboratory, and yeah, he got PhD from our laboratory, and he is now working for a private university in Tokyo. Anyway, so what we wanted to do with this research is the cut and paste operation for the fluid flow. So let's see an example shown here. So in this case, this one is generated by the numerical simulation. We see there is a sphere, and smoke interacts with this sphere. So what we want to do, for example, is that we want to duplicate this sphere region into this region by selecting this region and copy the region into this one. And then our method can achieve this result. And here is the animation. And in other case, sometimes we want to remove the sphere after the simulation. This can be possible by our method by selecting this region and copy it into this region. And here is the result. And this is the animation. Okay, the cut and paste operation is actually common in other media, like image or text, as shown in the slide. And our research in this case is inspired by this method, the Poisson image editing. This is one of the famous methods in computer graphics, and this method can naturally combine the images as shown in this picture. So we first we wanted to we tried this method to the for the velocity field obtained by the fluid simulation. So let's see this example. We have 2 data sets. One is the smoke interacting with a kind of sphere, and the other one is the more taller smoke. And we want to put this one into this region. When using the Poisson image editing technique, we should solve this minimization problem. And this technique can modify the velocity field, velocity inside the copied region, this region, to make the smooth transition between this region and the other regions. So however, we found that this approach did not work well. So let me show you an example. So this one, in this case, we want to copy this region into this region. And although it is not displayed, there is an obstacle in this region. And this is the result using the Poisson image editing. So let's see the animation. Yeah, you see the result is not realistic very much. It's not, the result is very different from what we expect. So the Poisson image editing technique modifies the velocity field inside the copied region. So the resulting velocity field is too blurry and the results are not very good. So our solution is very simple. So instead of modifying the velocity inside the copied region, we assume that the boundary region indicated by this white region, and we modify the velocity inside the boundary region only by solving this kind of slightly different minimization problem. Let me show you the same example, but with our method. Yeah, in this case, we can obtain the kind of expected and convincing result. Okay, let me talk some of the details of our method. So this is the minimization problem we want to solve. And after, through the several mathematical operations, we can obtain this equation, this formulation. We have two terms on the right. And the first term tries to minimize the vorticity. And the second term tries to minimize the divergence. The second term is good because this term corresponds to the divergence-free condition. So by minimizing this term, we can preserve the mass conservation condition. But the first term is not very good. So if we minimize the vorticity, the resulting flow becomes too smooth. So instead, we heuristically replace this term into this one. The difference, we want to minimize the difference of the vorticity to preserve the vorticity. So in this term, U hat represents that the advected version of the velocity that is computed at the previous time steps. So the first term, so therefore the first term tries to preserve the vorticity throughout the animation. So then by using some mathematical operation again, we can finally reach this kind of equation. This one is actually we need to solve. This equation is actually called a vector Poisson equation. So from this equation, we obtain three sets of scalar Poisson equations for each of the XYZ components. So we solve these equations using a conjugate gradient method. Okay, now let me show you some examples using this method. So firstly, this one shows the computation time. And if you look at this column indicates that the computation time for the optimization process in our method. And this column shows the computation time for the full simulation. So if you compare these two, our method is much faster than the full simulation. And particularly in this example, the computation time is 420 times faster than the full simulation. Okay, let me show you some examples. This one is the same one as the one shown in the beginning. So let me skip this one. I'll skip this one. So next one, this one, in this case, we have two velocity fields, this one and this one. And in this case, we want to copy this region into this region. So let's see the animation. So these are the input velocity fields. And here is the result. You can see that our method can successfully combine the flows with different turbulence. And the next one, in this case, we have a single input velocity field, this one, and we want to make the smoke taller by inserting the interpolation regions horizontally, like as shown in this figure. Let's see the result. And also we can create wider smoke in a similar way, like this one. Yeah, this is a similar example, but in this case, we want to make the tornado, creates the taller tornado. And this is the final example in this method, by this method. In this case, we want to make a large-scale sandstorm animation, but the simulation of the large-scale sandstorm simulation is very time-consuming. So we split the simulation into two, this one and this one. Let's see. And then we arrange these two simulated data set like this way. This one is placed at this place and this place, and this one is put in the center. And when we interpolate the velocity field at the boundary regions, this one, to make the smooth transition, and resulting animation is like this. Okay. Okay, let's go back to the main slide. Okay, next, I'd like to talk about this one, guided simulation. This is the our recent research result. So the guided simulation, yes, guided simulation was firstly proposed in these two papers. The same first author, I think that Nielsen invented this guided simulation approach. Anyway, the guided simulation framework, the user first prepares a kind of low resolution velocity field using the low resolution simulation. Since the low resolution simulation can be run in real time, so the user can design the flow interactively using the low resolution simulator. And the guided simulator uses the low resolution velocity field, this one and this one, as input, and synthesizes high resolution small scale details as shown in this picture. So if you compare this one and this one, and then the overall motion looks similar, but the high resolution details are successfully generated. So this method is very useful, and it is very convenient, particularly for the production environment. However, the problem is the computational cost. So this method works on the velocity space. That is, when the input velocity is specified, it is then upsampled, and the method solves a certain optimization problem to determine the velocity and pressure fields for high resolution grid. So therefore, the problem size becomes very large, so the computation is very expensive. Recently, these authors developed a much more efficient method. This method works on the frequency space. And that is, the input velocity field is transformed into frequency space by using the first Fourier transform, and then the high frequency details are added in the frequency space. So this method does not solve any optimization problem. So the computation is much more faster than the previous optimization-based method. And the implementation is very easy. So however, we found that this method does not work for non-physical inputs. So this is an example of such non-physical input. In this case, we do not use a kind of fluid simulation to prepare the input low-resolution velocity field. In this case, we manually create a very simple velocity field like this one to make the smoke form the arch shape as shown here. The previous method does not work well for this type of non-physical input, but our method can produce kind of convincing results. So let me show you some comparison. So this is the input velocity field. This is a kind of very simple velocity field. So here is our result. Yeah, our method can produce kind of realistic results. But if we use frequency domain method, this is a result. So the method does not produce, actually the method completely fails to produce convincing results. So this is a result obtained by using the previous or original optimization-based method. This looks good, but if you compare this one with our method, let me show you a side-by-side comparison here. So I think our method seems, the result obtained by our method looks more realistic. Okay, now let me talk about the details of this method. So the previous method works on the velocity field or the frequency space, but our method works on the stream function space. So stream function is actually computed from the velocity field. In our method, use the input velocity field by solving a Poisson equation. For 2D case, the stream function is actually a scalar function. And once we obtain a stream function like this one, then we can convert this stream function into the velocity field by applying a curl operator to the stream function. And the one important thing here is that by computing the velocity field computed from the stream function is completely divergence-free. So the mass conservation condition is completely satisfied. So our method works on this stream function. So after computing a stream function from the input velocity field, our method solves modified optimization problem, and we obtain the high resolution guided stream function. And then we apply the curl operator to the guided stream function to obtain the guided velocity field. Again, I would like to mention that this velocity field is completely divergence-free. So I think this is very important to create realistic results. So our method, we formulate our optimization problem to reduce the problem size. And as I shown in the previous slide, our method is applicable to the non-physical inputs. Okay, now let me talk more about the optimization process. So this is the formulation used in the previous original optimization-based method. So let's see this formulation in more detail. This term is the input velocity field, a kind of low resolution velocity field. And then this one is the advected version of the guided high resolution velocity field computed at the previous time step. So the previous method computes the velocity and the pressure field for high resolution grid. So therefore, the matrix size, the resulting matrix size becomes very huge. So the computational cost is expensive. So also the previous method needs to take into account this condition as a constraint. So we replace this formulation with this one. So if we compare this one and this one, so actually we replace this term into this term. We use the stream function here. And our method determines the stream function. And as I mentioned in the previous slide, by computing the velocity field from the stream function, the resulting velocity field is completely divergence-free. So we do not need to take into account this condition anymore. So however, this formulation does not reduce the problem size very much, because the stream function in 3D case is called a vector potential, which is a kind of vector function, and the dimension of the vector potential is the same as the velocity field. So the problem size is not reduced very much. So in order to reduce the problem size, we heuristically introduce a scaling function W here. Scaling function is a scalar function. And we use existing or pre-computed stream function, this one. So the scaling function is a scalar function, so we can reduce the problem size. And for the stream function, we use the stream function computed from the input velocity field. So furthermore, we introduced an additional term, this one, kind of regularization term. So this term works as a control to allow the user to control the effect of the guiding, and alpha is a control parameter. By choosing larger value for this alpha, the resulting guided velocity field becomes similar to the input velocity. Okay, now let me show you some examples. So this one is uses a kind of non-physical input. In this case, we want to make the smoke form the circular shape. This one, this is the input velocity field. And here is our result. A realistic motion is obtained. And if we use the frequency domain method, again, the method does not work well. And this is the side-by-side comparison. Next one, in this case, this is an example of a branched flow. Again, this is a non-physical input. This is the input velocity field. Then this is our result. And the frequency domain method does not work. Yeah, this is side-by-side comparison. Next one, this one, I think this one is a kind of interesting. In this case, we use the same input velocity field as the one shown in the previous slide. This one to make the smoke form the arch shape. But in this case, we put the obstacle, in this case, a sphere in the center. And during the optimization, we take into account the effect of the obstacle. Then we can obtain this kind of realistic results. This one is a more practical example. In this case, we try to generate whirlwind smoke. Yeah, and the input velocity field is also generated manually by ourselves. Okay, finally, this one is kind of actually the comparison using the physically based input. That is, we use a numerical simulation, fluid simulator to prepare this input velocity field, and we compare our results with the frequency domain method. These two are generated by using our method, and these two are generated by the frequency domain method. Let's see. So when using our method, the results changes depending on the control parameter alpha. If we choose larger alpha, the resulting motion of the smoke becomes similar to the input smoke. And if you choose smaller value, then the results become slightly different from this one. Yeah, and for the frequency domain method, this method also has a single parameter that is a cutoff frequency shown here. So we need to choose appropriate parameter for this cutoff frequency. If we choose inappropriate parameter, in this case 1/4, the result is not realistic very much. But if we choose appropriate parameter, in this case 1/12, then the result seems the best among these four. So I think if we prepare the input velocity field by the numerical simulation, the best choice may be the frequency domain method. But if we use a non-physical input, our method may be better. Okay, and that's all for the contents. Let me conclude the presentation. So we have proposed a method for improving the directability by, we have developed a method for controlling the simulation. And in this talk, I didn't show any results, but we have developed a method for modeling fluid volume from a single video. And we also developed a method for reusing the existing data set. And as for the future work, we want to extend these methods to different natural phenomena, like clouds or fire or something like that. And we are also interested in the sterilization of the simulated synthetic fluid phenomena. Okay, that's it. Thank you for your attention.
Okay. Thank you for Professor Daobishi for the talk. Okay, any questions? Seems that there's no question from the audiences. So if there's no question, so I may ask some. My first question is that for the fluid cut and paste. So yes. If I am not wrong, the Poisson equation is actually solved at the boundary, not in the whole region, right?
Right.
Then why solving the Poisson equation at the boundary can make the pasting more realistic than solving the solving the Poisson equation at the whole region? So I just want to know the reason behind.
I see. I think that if we solve the Poisson equation inside the copied region, the velocity field becomes how to say kind of all inside the boundaries, the velocity field, all the velocity is modified and kind of smoothed out, so the resulting flow becomes something like this. I think that's the reason.
Okay, so but there should be some thickness of the boundary to be determined, right? So for solving the Poisson equation, right?
Should be what?
There are some thickness. I mean,
yes,
so
exactly.
yeah. So how can the thickness to be determined? So is this an empirical value or some kind of guidance on the determination of the thickness?
Yeah, it's actually we have no. It is actually determined experimentally. We have no clear solution to determine the size of the boundary region.
I see. So that means that for different applications or different scenarios, this value should be chosen numerically according to that kind of a scenario.
Yes, exactly.
Okay, thank you. And my second question is about the last talk about the fluid guiding. So yes. According to your formulation, there is a weight, W, in the minimization process, right? So my question is that the first is that how this weight can be determined?
Yes, actually, this is the unknown variable. We optimize this variable to minimize this energy function.
I see. This is to be determined, to be solved, right?
Exactly.
Okay, I see. And then you compared your technique with a frequency domain method. So I just wonder why frequency domain method can fail for many cases.
Yeah, that's a good question. Actually, we try to find the exact reason, but yeah, actually, we don't know why. Maybe the maybe the non-physical for non-physical input like this one. Maybe the frequency in frequency space there should be some discontinuous frequency. That may be the reason. We need to investigate more.
Okay. Thank you. Okay, I have no questions. So see whether there are some other questions. Okay, if there's no other questions, let's proceed to the next talk. Okay. So the second talk is about the modeling of a fluid-solid mixture with a smooth particle hydrodynamics. And the speaker is by Bo Ren, Professor Bo Ren from Nankai University, China. And Bo Ren received his BS and PhD degrees from Tsinghua University, Beijing, China, in 2010 and 2015, respectively. He is currently an associate professor at the College of Computer Science, Nankai University, Tianjin, China. His current research interests align in learning-based, physically based simulation, 3D scene geometry reconstruction, and analysis. So let's now welcome Professor Ren to talk for his talk on this topic.
Thank you, Professor Liu. And let me share my screen. So, okay, I think it's okay. Okay, welcome to this talk. I'm Bo from Nankai University, and my talk is about modeling fluid-solid mixture with smooth particle hydrodynamics, namely SPH. Yeah. Well, the real-world multiple fluid phenomena is very common, and we can observe whether it's interfacial flow or some miscible or dispersed fluid mixtures in our daily life. These are some pictures I just downloaded from the internet, and we can observe such as oil-water mixture on the bottom right, or cocktail wines on the bottom left. These phenomena are very common in our daily life, and simulating multiple fluid has a long history in computer graphics communities, and there is a decent variety of researches ever since I think ever since 2003. Actually, first of all, the very first papers are on interfacial flows, and later or recently since 2014, there are some miscible. Since 2010. There are some miscible flow works, and these works are concluded in a survey we previously wrote, and if anyone are interested, you can just refer to it. And today I will talk about using SPH, namely the particle-based method, to model the multiple fluids. Well, the fundamental equations to calculate the multiple fluids is they are just like this. The multi-fluid Navier-Stokes equations. Well, these are the phase-wise equations. The continuity equations on phase K, and the momentum equations on phase K as well. So comparing with the single fluid NS equations, we can find that there's a alpha K value term in this equation, which is the concentration, or more specifically, the volume fraction of this multiple fluids. Well, the volume fraction concept is very easy to understand, because our air, we are breathing the air, it contains about 21% of oxygen and about 79% of other gas. So this is the concept of volume fraction. And but well, if these phases can mix together, well, we will call them a miscible flow. If they cannot mix together, we will call them an interfacial flow. For example, the mixing of oil and water are interfacial, because you can find a lot of interfaces between these two phases when they move. And if you mix, for example, alcohol with the water, you will see no interfaces within it. Or if you look at a cup of cocktail wine, you will see you will see mostly no interfaces between the colors. So traditionally in computer graphics, the interfacial flows are dealt very easily with the single phase equations, because you can just treat each region that contains one phase to be guided with a set of single phase Navier-Stokes equations, and you just need to handle the boundaries or handle the interfaces. You can track the surfaces, or you can handle the boundary conditions to get a good simulation of these interfacial flows. But if they can mix together, the things could become more complicated. And we will talk about mainly talk about the miscible case, and mainly in Lagrangian methods, because, well, in CFD field, in CFD computational fluid dynamics, they have simulated the miscible phases in grid-based methods for decades. So I will talk about our graphics approaches in particle-based methods, which are friendly to parallelize and faster. Well, as we just have seen that on the base level, there is a set of full multiphase model. You need to calculate the phase-wise equations of the Navier-Stokes equations. And this model is, we can call it the full multiphase model, is very most fundamental, but it has the drawback to that it's hard to complete. You usually need many assumptions to complete these equations and get an implementable algorithm. Well, with some simplification, you can have the mixture model, the so-called mixture model, and this mixture model has the has the this mixed model has the feature that it can analytically compute the relative velocity between these phases, and the mixture change, the mixture values will be computed from this relative velocity directly, and have some miscible flow effect. And finally is the homogeneous model. And this model assumes that we have some, all the phases are moving with the same velocities. And this model is the most, the easiest to compute, but it also discards some important effect that multiple fluid phenomena has. So I will talk about them one by one in the next talk. So talking about the traditional or conventional ways to for mixed for multiple fluid simulation, we can think about the simple diffusion models, which means that we just calculate the diffusion equation between the phase form fractions, and these form fractions will change according to time, and the diffusion equation will give us some good results, but it will not be enough for complex phenomena. And as I have mentioned, the homogeneous model will replace this diffusion equation directly in the red dashed line, and the mixed model will replace the calculations in blue dashed lines, which the mixed model will solve the continuity equations directly. So this is the mixed model. On the equation below is the momentum equation, the phase-wise momentum equation we have just seen, and if we sum them by one fraction of k, we sum the k equations together, and we will get a mixed momentum equation, which we use the aggregate or average velocity, average density of the mixture to have this mixture equation. Well, these terms in phase-wise equations will sum up to be the corresponding terms in the mixed model equations, and a similar summation applies to the continuity equation, which we will say that well, this continuity equation is very similar to the single phase one, but there's an important difference that we cannot assume the mixed model in the mixed model that the divergence of any velocity is 0. We cannot assume that. The reason I will talk about the reason in later slides, but now currently let us move on. Well, this similar summation is not very usable. It's not very useful in actual implementation. In the actual implementation, we use this kind of phase-wise equation derived from this phase-wise continuity equation, and the difference is that we use the average velocities here instead of the phase-wise velocities. So it's just some math derivations, and combining this continuity equation and the momentum equations, we can have the equations for the mixed model, and among them, this drift velocity can be analytically solved by some, well, this may look quite complicated, but each of the terms in it can be calculated analytically, such as the phase case density, which we can assume is constant, and the phase case pressure, which can compute it from the particle pressures in the SPH, and these are the volume fractions and mass fractions. So this drift velocity can be calculated analytically. And if we have this drift velocity analytically calculated, we see that if we use some explicit solvers, such as the most conventional SPH do, we can solve this. We can solve these continuity equations, and we can solve these momentum equations. So there is an example here. Originally, there are well, I think there is about 8 phases in this example, 1 transparent and 7 colored phases. So, well, this is the mixed model, and let's first move on to the homogeneous model. And let's think about the simple diffusion model. The conventional simple diffusion model. What's the advantage and the disadvantages of diffusions in our solver? Well, the pros are the diffusion is very fast. It's very stable, and we almost always know how diffusion will go, how diffusion directions will go, which means it's very predictable. But the downside will be that the diffusion is non-reversible and unstoppable. You will never stop a diffusion before all the colors are mixed together, and the result is very, which results in a dull color. And well, a better model uses energy-driven mass diffusion instead of this diffusion. Well, you can think of it as a better diffusion model, which uses the so-called Hilliard model. And the equations are like here. The first 2 equations are what we the single phase, almost the single phase Navier-Stokes equations we are very familiar with. And the third one is, well, it has the form very similar to the diffusion model, which where we can see that there is a difference here. We have a mu k, which is chemical potential. It relies on the mass fractions and so-called Helmholtz free energy. This one, this Helmholtz free energy is something related to the physical state of the fluid mixture, which is which can be user defined, but it says that each state, the state is defined by the different volume fractions of each phase, such as we can say one state maybe if a 3-phase mixture exists, we can define one state to be 0.3, 0.3, 0.4, and another state will be 0.2, 0.5, 0.3. Which are the volume fractions of these three phases, and each state has energy. Each state is related to an energy using this Helmholtz free energy. One example is shown here, which means from the state 1, from the mass fraction 1, mass fraction 2, mass fraction 3, we can compute energy at this state. The in physics, there's a law that that is any physical system tends to move from high energy state to low energy state. So the physical, so if we define this Helmholtz free energy to this form, the fluid system will tend to move to a mass fraction state, which satisfies, which meets the minimum point of this FC. On the right, we can see that there are two local minimums, which are the red dots, and the global local minimum is on the 0.5, 0.5 state. So we can predict that the final state, the final state will be this one. If we see this red, green, blue color, if we render this red, green, blue color, we will see that an initial fluid mixture will eventually goes to the final state, which is the red will stand. Let's see. I think. I think the second state is rendered red. Red will stand out, and blue and green will mixture half by half. So this is the effect of Helmholtz free energy, and this is another result of mixing mixing two fluids together, which one is the egg yellow and the other one is the water. Okay. There's a recent adoption of this theory, which appears in Dr. Chen's 2020 paper. Well, their paper is on reducing the calculation errors using MLSRK interpolation of the for the SPH assimilation, and they use the NSCH equations for multi-phase concentration evolutions, and below are their results. So let me compare this this so-called mixed model or Navier-Stokes calculated model. Well, the energy-based model, which I just shown, is much faster because you don't need to calculate the phase-wise continuity equations. You just need to solve a diffusion-like equation, and that is all. So it's a bit faster, and it is theoretically easier to satisfy incompressibility because you will see that the momentum equation is very similar to the single phase one, and it says if you assume each phase are moving at a if you assume all the phases are moving at the same velocities, the divergence of the velocity fields becomes zero again. So you can just use such as PBF or any other techniques to that applies to single phase simulation to enforce incompressibilities in such works. And currently, the third one is that it applies to extraction, but it has also some drawbacks, which is the advantage of the mixed model. If we face this unmixing back motion, you will see that well, these several phases are actually immiscible, but originally we manually set them to be mixed in a mixed state. The SCH calculation will first produce dispersing drops before unmixing them into later layers. But the mixed model will will be more natural. The result of mixed model will be more natural and in the layering process. So there are some side steps for this for these multiple simulation methods. The first one is that we can exploit volume fraction to have some post-simulation process according to the existing simulations, and because especially for bubbles, I mean, bubbles have this this feature that when you look at the because it's gas liquid mixture, when you look at the mass fractions, you will see that the liquid fraction, the fraction of liquid is dominating. But when you look at the volume fractions, you will see that the gas fraction will be dominating. So we can calculate this difference between this mass fraction and volume fractions and re-render the existing simulations to generate bubble effect. Or we can see that we can add bubbles to existing multiple fluid simulations. This is a result. The second one is that we can integrate the multiple fluid concept into other physical systems, such as the shallow water equations, and to generate some dissolving surface effects. These are the equations we used in a previous paper, and this is a result. We can see that the bottom color will be dissolved during this water flowing, and it will stick to the solid surface when the water flows over this region. So, I just mentioned that the homogeneous model has some advantages to enforcing incompressibility. Well, it also means that the incompressibility is an issue to the mixed model because the compressibility. Well, there is a hard question: is that what is the incompressibility we are talking about? If we think it in more carefully, we can see that the compressibility can be physical. Because if we have reactions, if we have phase transitions, water can turn into gas in some extreme cases, or not extreme. We observe it in our daily life, but in our simulation, it's kind of extreme. This is certainly not non-physical. So what is non-physical incompressibility? Well, I think they are due to the numerical calculation errors in our solvers, whether it is the drawback of the model, or whether it is the drawback of our implementation. So such non-physical incompressibility is what we want to eliminate. But for multi-phase flows, the physical compressibility is common, and we want to model them, or we need to model them in our simulation. So we need to tell them apart ultimately. But however, there are several methods currently to handle the incompressibilities in multi-phase simulations in SPH. The first method is using the homogeneous model. We just have seen it. The second method is that we change the definition of the integration velocities from the the original integration velocity is balanced by mass, or we can see the mass-weighted integration velocity. The new definition of this will be volume-weighted, or so we can observe the difference is that whether we multiply this UK with rho, or we can see that one integration velocity is the speed of the mass center, and the other is the speed of volume center. So if we use the new definition, we can prove that the new metric under the new definitions, we can prove the integrated velocity divergence will again be 0. So that will be a very good news. It seems a very good news because we can use previous single phase methods again, such as ISPH or the FSPH or etc. Well, during the process, we need to follow some similar derivation steps used by the previous definition, and derive a new momentative equation and new continuity equation. But this step is not very hard. So this method is adopted by Dr. Jiang in 2020s, and this is the result. Well, this is their result is very good, and the method is very practical for graphics use. But there's a problem. The advantage is that it is easy and simple, and directly use single phase conventions of incompressibility, incompressibility Hammond. But the drawback is that this assumption is not very physical when we use the constant mass SPH. So let me show. Let us consider this toy example. If we have two phases, a green phase and a red phase. Green phase has a smaller density, and the red phase has a bigger density. And all the fluid are still. They don't. All the particles do not move, and they only depart from each other due to gravity, and in a immiscible phase, which means you will in the end you will see green particles above the red particles. Suppose originally they are mixed with 50% to 50%. So it's I use yellow dots to represent the initial particles. And finally, you will see that the red dots will lie above the the green dots will lie above red dots, and inevitably the green dots, the green particles will be will occupy a larger volume than the red particles, because the particle mass are the same, and the green ones have a lower density value. So what happens? In the green region, the volume expands, right? In the red region, the volume shrinks. So from the initial state to the final state, inevitably you will see some divergence during this change. So the actual physics is not divergence free when we use the SPH simulations. So the method 3 is that we proposed a method using deformation gradients, which do not assume any, which do not meet any divergence-free conditions. So we just think that the deformation gradient can be used on fluid simulations, and the Jacobian of the deformation gradient can be calculated by the volume fraction change of the of one particle. Because if we think of inside one particle situation, if phase case volume fraction is smaller than the last time step, it is equivalent to this phase is expanding within this particle region, within the matter volume represented by this particle. So we can prove that the JK, the Jacobian of the deformation gradient, local deformation gradient, corresponds to the volume fraction change rate. So this is derived from the continuity equation. And if we look at the momentum equation, we can directly compute a deformation gradient from this the physical definition. So we can match these two. Changes. One due to the velocity field and one due to the concentration change together, and derive a set of linear equations and solve it. So finally, we can integrate our method into readily into the IISPH framework as well. The final equations are very similar to the original IISPH single phase version, and we just saw a similar AP equals to B linear equation for the corrective P values on the particles. So these are the results. We can the figure in the red lines are our results, and the other two figures are from previous compressible simulations. So we can observe that the compressibilities are reduced, and the particle layering, the particles are much more ordered during the simulation as well, using our approach. This incompressibility works also has side steps, which mainly the method 2 assumptions are used in recent works, also by Dr. Jiang in 2021. He goes back to the fundamental full models and with the assumptions of his method 2, and proposed a direct solver to give more rigorous results of the phase fixed mixing effect. So, well, another issue of the mixed model, or another issue of the multi-phase flows, is solids. We want to put solids into the simulation with fluids together. So if we think of handling solids, or I can say handle sand-like solids, it's quite straightforward to add these solids into the mixed model by just adding one term into the momentum equations. This one is from the solid theory, actually from the solid model. You know that in fluid you will calculate the viscosity or the Gaussian or the divergence of the Gaussian stress tensor. And in solid theory, there's a similar term. So just combining them together will lead to a mixed model which can handle solids. And you can add a dissolving equation to determine when and how much a solid can turn into fluid phase. So if I show it with a chart, it's just like this. You combine the SPH multiple fluids method and with SPH solid theories, and you can obtain a theory which can handle both solid and fluid together. And this is a video. So after pouring the water into the tank, you can see the coffee and candy are dissolved into the water. So there's an issue here because this solid model still assumes that the liquid follows the same NS equations when it mixes with the solid. Well, this is not a very big problem if we are treating with sand-like materials because well, they can be considered as fluid as well when we trigger them. But this is not always the case, especially in if we are dealing with porous sponges. Inside the porous sponge, the fluid follows Darcy's law. It's not quite the same with the Navier-Stokes equations, and how can we handle it? Let us consider what can a mixture be first. So, or I can say, let us consider how can we exploit the mixed model. Well, firstly, a mixture can be a mixture of phases. Secondly, well, these phases can obey a mixture of physical laws, which can be different from each other, very different from each other. But thirdly, these phases can go freely across a mixture of so-called law regions. In each region, we have a set of different laws, and the phases obey these different laws according to the regions. Well, the problem is when we are using SPH, when we are using particles, we have one particle that contains several phases. How do we change a multi-phase particle state? Its positions, its volume fractions of phases, its densities, etc., when it goes across region boundaries. Or in more details, a sponge will absorb, let us consider a toy example. A sponge absorbs phase A more quickly than phase B. In addition, they have different permeability values inside the sponge. For example, phase A can move much faster than phase B. Where should an SPH particle go on the boundary? And how is the concentration changed? And how can these two match with each other? Please note that if you move a particle on the boundary to a new place, ideally, if the particle is half out, half in the boundary, it should have 50% A, 50% B, or something like that. If as the particle moves inside the solid, the phase B should decrease. The volume fraction of phase B should decrease within this particle, and finally it will contain only the phase A volume fraction. So how can we ensure the consistency between this momentum change and or position change and the continuity or volume fraction change. So recently we just used we just did some research on this, and I will talk it about from the next slide. And before it, let's consider some simple approaches. Conventionally, for single phase particles, we can absorb single phase particles to when the particle meets the solid surface, and generate a new particle or add the particle mass to the so-called solid particles concentration. We can delete this, and we can insert new particles to when the liquid is squeezed out from the solid. But in the multi-phase case, it is very exhausting. First of all, you will delete fraction by fraction the particles, and when you insert a new particle, you will result in many more small or big particles with different sizes. It is very exhausting to handle in implementation. And if you add some merging or splitting strategies, it will be more complicated and not very stable in multi-phase case. And still, we want some fully coupling between multiple phases regions and with the solids. So how do we do it? We just solve this problem using the mixture model and introduce a concept of virtual phase. We will treat the in our work, we treat the inside and outside parts of the same phase as two virtual phases. So one phase will correspond to one inner phase and one outer phase in our simulation. And the action of liquid moving in or out and phase mixing or unmixing are uniformly considered as virtual phase changes calculated by the mixed model. So all the problems, all the issues we mentioned in the last two slides are automatically solved by this mixed model kind of simulation with virtual phases. The particle behaviors on the boundary are shown as in this figure. When the particle comes near the solid surface, in this case, we said that the yellowish phase can be absorbed, but the greenish phase cannot be absorbed. And the particle moves towards, as the particle moves towards the solid surface, the light yellow phase, which is the outer phase, can change into the inner phase, which is the deeper yellow phase, and due to the absorption flux effect. And each phase is subject to one set of physics equations. The outer phase is subject to outer physics, and the inner phase is subject to inner physics. And the particle will be influenced by all the acceleration effects experienced by the phases from different laws. So and the concentration change is calculated by the mixed model itself. So these are the equations. The first two are the continuity equations, very similar to the original mixed model, and the last term is the boundary absorption flux. The third equation is the momentum equation of the particle, and all the there are several acceleration terms in addition to the gravity term. The second one is the pressure. The second one is the pressure term in the outer region, The third one is the pore pressure term, which is corresponds to the pore pressure due to the Darcy's law in the inner region. The fourth term is capillary acceleration in the inner region, and the final term is all other external forces. So this, the right hand of this momentum equation is just adding all the effects together to influence the particles' mass center motions. There is a slight modification to the original drift velocity. But the original drift velocity in the original drift velocity calculation, there is a pressure term here, or I can say there's a term corresponding to pressure gradient here. Well, the Darcy's law, the QK is just a pressure gradient in the Darcy's law. So, no. The QK is proportional to the pressure gradient in the Darcy's law. So we can just use this QK in the Darcy's law to replace the original pressure gradient to make the inner drift velocity calculation completed. So the drift velocity calculations in the outer space are the same with the original mixed model. So we have this set of new equations. We solve them, and we can automatically solve all these issues: where and when, how, and how much particles move in and out, and how does the concentration change. So till now, I just talk about the Darcy's law, but this approach can extend to other more complex theories. Because if we want to, if we look at the momentum equations, if we look at the momentum equation, we can see that, well, actually, any effect will influence the fluid particles as an acceleration effect. It will appear as a different acceleration term or more acceleration terms. You can just add them in this momentum equation. On the other hand, these modifications, I just mentioned that I used the Darcy's law, which I used the Darcy's law's value, which is proportional to the pressure gradient inside the solid region, to modify this drift velocity inside the solid region. If you are facing with other physical laws in other physical regions, well, any set of physical equations involving fluid almost always contain a pressure gradient driven effect. So you can just substitute them into this place, and you'll get new drift velocity calculations for that effect. So these modifications to the original mixed model is quite extensible, and it has the possibility to apply to more complex theories. These are some results of our work. So in both cases, the solid only absorbs the red liquid and leaves the green liquid outside. Well, originally on the left, the red and liquid and the green phases are mixed together, and on the right they are separated. So we have open sourced this work. Well, you can find the open source code on our homepage, and well, there's a final video. I think this open source code is the first multiple fluid open source one on the internet till now. So if you are interested, welcome to have a try. Thank you, and that's all.
Okay, thank you, Professor Boren, for the talk. Any questions? Let's have a look at other questions. So any questions from the audience? Okay, if there's no questions from the audience, so I have several questions. Okay, so in this talk, initially you mentioned about the Navier-Stokes Cahill equation. Right? So are you using this in some of your research you mentioned here? Did you use this kind of a model equation to solve the multi-phase flow problem?
Yes, yeah. yes. So this, do you mean this? Yeah. Actually, we published one. I just saw it in the last talk. One photo in the last talk. Yeah. We published one in 2015 on the graph.
Oh, okay, I see. Yeah, I see. Yeah, my question is that regarding this, so according to my knowledge, okay, the Cahill equation has a high order, the fourth order derivative equations. So it is more likely to have a large dispersion error during the simulation, right? So in the literature, there are some other formulations. For example, the Allen-Ken equation that can be replaced for the Cahill equation. So have you considered that kind of equation in your later research?
Well, not yet. To be simple, not yet. We have not considered them. Well, I agree. It's quite an interesting topic.
Okay.
But
okay. Thank you.
The issue is that those equations can what different effects can those equations bring? You know, this CH equations are pretty fast currently, and well, pretty stable, I think. And I'm not sure how much benefit will other models bring.
Yeah. For example, if you consider some kind of a more turbulent flows, whether this kind of lower order model can benefit for higher stability and accuracy.
Yeah. That's really
maybe this is a case.
Topic. Yeah. But another issue is that if you're using SPH, the turbulence and single phase SPH turbulence is not very well resolved yet.
Yeah.
So for multiple phase, it's more complex. So I think it's very interesting, and it deserves future research. Yeah.
Okay. And my second question is that you also mentioned about enforcing incompressibility in II-SPH, right?
Yeah.
So I want to know that what's a key idea of this kind of incompressibility enforcement in II-SPH, because you didn't mention that, and also how the incompressibility can be satisfied at a solid boundary, because I also saw some kind of coupling examples.
Yeah. It's my fault. I just omitted all those parts because they can all be found in the II-SPH paper. So the II-SPH, is for single phase. It's just based on single the divergence-free assumptions and or constant densities assumptions of the single phase fluid simulation. And the two works I introduced in this talk are for multiple phases, and actually we extend the we extend the theory, or we extend the framework to multiple phase. Yeah. So I can see that the boundary handling is also very similar to the ISPH one in the same form, but well, the full mathematical derivations are very complex. So it's not very easy to talk about them in these slides. But the final forms are very similar to the ISPH work. You can find them also in our papers.
Okay. And my final question is that, so have you considered about involving a grid into the solution process? For example, if you solve the concentration equations using the grid while you use the SPH for the fluid equations, so that may be, I'm not sure whether it will be beneficial or just the same.
Actually, it is also very interesting. We have not tested the grid, but well, you know, this is quite similar to current hybrid methods, right?
Yeah. It's kind of a hybrid method.
So I think it will be possible to use some current approaches. Actually, there are some multi-phase SPH. No. There are some multi-phase NPM works. However, these works has some drawbacks that NPM can these multi-phase NPM works are using simple diffusion equations for the phase concentration change for the phase mixing effect. There are 12 papers in this NPM, use NPM. Yeah, I didn't put them into this slides, which they're mostly done by the Tsinghua University, and they use simple diffusions, and well, there are some difficulties, I think.
Okay.
But I think well, difficulty. There are difficulties, but they deserve more research in the future. There are challenges, but there are opportunities as well.
Okay, I see. Okay, then I have no more questions. So, so see whether there are some more questions from the audience. So if there's no more questions, and then the session of this talk is here. So we welcome the two professors to give the talk today. Thank you.
Thank you.